Okay, let's look at homework set number 8. The first question is, show f of z equals e to the z bar is not analytic anywhere. So you probably knew how to do this in the past. All we need is Cauchy's Riemann equation, and you need to extract then the real and the imaginary parts of e to the z conjugate. So that one will follow straight from Cauchy-Riemann. Number 2, second one. Why is the real part of e to the 1 over z harmonic in every domain that does not contain 0? The plan on this one is consider the function f of z equals e to the 1 over z. Where's that analytic? And why? Maybe hint prime. Where's it differentiable? You know how to differentiate e to the 1 over z. Because you know the chain rule, you know how to differentiate 1 over z, and you know how to differentiate the exponential function. See where this function is differentiable? I think that's going to be on a domain they've asked about. And you know differentiability, but why? It implies analyticity. So if we've got differentiable on an open region, we've got analytic on the open region. It's our definition of analytic, actually. So you'll check this function for analyticity by checking for differentiability and conclude that, hey, we got an analytic function in this domain they're talking about. This is the real part of an analytic function. What do you know about real parts of analytic functions? I think that's where theorem 2.26.1 will come in handy. The graduate problem is actually somewhat similar to this. It says let f of z, I've handwritten this, f of z is lowercase u of xy plus I lowercase v of xy for real and imaginary parts. Let this be analytic in a domain D. Y is capital U of xy, defined as e to the lowercase u of xy times the cosine of v of xy, and capital V of xy, defined to be e to the u of xy sine v of xy. Why is that harmonic in domain D? So we've taken the real parts of f and made them exponents of an exponential function, and we've taken the imaginary part of f and put it inside a cosine function and a sine function. Well, for a hint on that one, consider the function g of z equals e to the f of z. You know, if you were to compute e to the f of z, that would be the exponential function with this inside of it, and find the real and imaginary parts of that. I think these guys would look familiar. So, consider this function. Where is e to the f of z analytic? Can you differentiate it? You can differentiate the exponential function. Can you differentiate the f of z function? Yeah, we were told it's analytic on D, so it's differentiable on D. Exponential function's differentiable everywhere. Chain rule, tell you that you got yourself a differentiable function, you got yourself an analytic function wherever the given function f was analytic on domain D. Now the question was about harmonic, not about analytic. But as in the previous one, if you'll look at theorem 2.26, it's 2.26a instead of 2.261, look at the appropriate result concerning harmonic functions. The real and imaginary parts of an analytic function are harmonic, is the result we need for both of those. The next one for everybody, 3.33.3, show the log of I cubed doesn't equal 3 times the log of I. So those rules you're familiar with from the real setting. They don't always hold. You know, we've been through all this stuff with multiple valued functions and so forth. This is the principal value of the logarithm. It's an analytic function on the appropriate domain. It's a function. It's single valued. Principal value of the log function. So just compute both sides. Use the definition of capital L logarithm. Compute both sides. They won't be equal. My hint is compute and ... coterminal angles. Something will go on with coterminal angles that will make the values different, but they're going to be related in a coterminal angle way. So there'll be some coterminal relationship between arguments on both sides, I think is what it is. But the values are different. The last one says consider f of z equals principal value of the logarithm, z minus I. Show this is analytic except on the portion x less than 0 of the line y equals 1. The main reason I wanted to do a video was so I could draw pictures of this stuff here. So what they're saying is this function log z minus I is analytic except along the line y equals 1. That'd be a line parallel to the real axis and correspond to imaginary part equal to 1 along here. And then we took the x part to be non-positive. So it'd be this little piece here, the line they're talking about. So we'd include the point I, and then we kind of peel up, remove a line, a horizontal line that has imaginary part equal to 1 from real part equals 0 to negative infinity. So that's the question. Show that this microphone wardrobe malfunction. There we go. Show that this function is analytic except along that red line. Well, you know where the capital LOG logarithm function is analytic. We defined it to be, we defined the principal branch of the logarithm on the whole complex plane except for 0. And then when we looked at this as an analytic function, we removed the non-positive real numbers. We removed the origin, of course, 0, because, well, logs aren't going to be defined at 0. Exponentials are never 0, even in the complex setting. And we remove the negative real axis along with the 0. So that's what we had for the domain of this function. Well, what's the relationship between capital LOG of z and capital LOG of z minus I? Well, you've replaced the z with a z minus I. So we've effectively, apparently, taken this domain and shifted it up by 1 unit to produce that domain. Does that make sense? When does this function think it's looking at 0? When the z value is I. When does this function think it's looking at 0? Well, when z is 0. So there's a correspondence between, I leave it to you to come up with some explanation more logical than this. But this function is undefined at 0. We have a problem when z equals 0. Well, this function has the same problem, but that problem occurs when z equals I. So in a sense, there's a correspondence between 0 for this function and I for that function. When you do phase shifts for trig functions, you usually think along those lines as well. But should be good to go on those 4 or 5 problems, given those hints. And we'll talk about them in class next time if necessary. Bye-bye.